Hello everyone. Now we will be doing the topic of errors and measurement. Small topic, scoring topic, and question from here comes every year in NEET. So do the topic carefully. So without wasting time, let's start errors and measurement. So first thing we need to talk here is called the order of magnitude. If you have got any quantity written in the format of a into 10 raised to the power of b, if you have got any quantity written in the format of a into 10 raised to the power of b, rewrite the quantity such that the quantity a lies between 0.5 and 5. Let's take the example of 1 mole. 1 mole means 6.023 into 10 raised to the power of 23. If you need to find the order of magnitude of 1 mole, how will you find it? The rule says rewrite the number in such a way that a lies between 0.5 and 5. Here you can see the first part 6.023 is more than 5. So rewrite it such that this value lies between 0.5 and 5. How to write? You can rewrite this number as 0.6023 into 10 raised to the power of 24. Now you can see this first part lies between 0.5 and 5. So how to find the order of magnitude of any quantity? Rewrite the quantity in the format a into 10 raised to the power of b such that a lies between 0.5 and 5. When you write quantity in such a way, then b is the order of magnitude. So for 1 mole, the order of magnitude is 24. Okay. So let's practice some question here. First question. If the number is 4.3 into 10 raised to the power of 5, what is the order of magnitude? You will look at this first part and say, sir, 4.3. 4.3 is already less than 5 and greater than 0.5. Then this part B must represent the order of magnitude. Hence, the order of magnitude of 4.3 into 10 raised to the power of 5 is nothing but 5. Next question. What is the order of magnitude of the number 6.2 into 10 raised to the power of 7? So 6.2 into 10 raised to the power of 7. Here you can see this part 6.2 is more than 5. Then sir, what to do? Rather than thinking of 6.2 into 10 raised to the power of 7, think of it to be 0.62 into 10 raised to the power of 8. I think you are able to understand that both are one and the same thing. But now this first part lies between 0.5 and 5. So the order has to be nothing but the power of 10, which is 8. So the order in this case has to be 8. Let's take one more example to understand. If you have got number 9.3 into 10 raised to the power of 12 and you need to write its order, you will say, sir, 9.3 is more than 5. I need to rewrite this number such that the part A, the first multiplying part, lies between 0.5 and 5. So when you rewrite, you get 0.93 into 10 raised to the power of 13. Writing it this way, you get into 10 raised to the power of 13. So the order has to be nothing but 13. Simple. Let's move to the next article. Rounding off. I know that you have learned rounding off, I think first time in class 6th or 7th. It's really easy topic. But let's see it once before we move on to the next heading. Rounding off simply means approximating the number closer to it. Rounding off simply means approximating to the number closer to it. What is the meaning? Let's see. For example, if you have 673 and you wish to round it off to nearest 10, which are the nearest multiplier of 10 to 673? So you will say, sir, one is 670 and one is 680. So if you wish to round off 673 to the nearest multiplier of 10, you will think of the nearest multiplier of 10 to 673. That will be 670 and 680. Now tell me, 673 is closer to 670 or 680? If you think of the number line, definitely 673 is closer to 670 than when compared to 680. So when you try to round off, you will definitely round off 673 to the number closer to it, that is 670. As 673 is closer to 670, then 680, it will be rounded off to 670. Now let's say, if we wish to round off to nearest 100, what are the nearest 100 to 673? So think of the number line. Here you have got 673. What are the nearest multiplier of 100 to 673? So you will say, sir, there is somewhere 600 and there is somewhere 700. So visualize the number line. Which one is closer to 673? Sir, the nearest 100 to 673 is 700. That's why when you round off to nearest 100, you will say that 673 can be approximated to 700. So as 673 is closer to 700, out of 600 and 700, hence it will be rounded off as 700 if you have to round it off to the nearest 100. So let's do some examples. Round off the following to two places after the decimal. So you will get multiple numbers. You have to round them off to two places after the decimal. Let's see the first example. If you have got 6.834 and you have to round it off to two places after the decimal, you need to drop this one, the last four. What to do? You can think the numbers closest to 6.83. If you think of 6.834, it will lie somewhere between 6.83 and 6.84. So 6.834 lies between 6.83 and 6.84. Now question is 6.834 is closer to 6.83 or 6.84. Sir, after the 3 now we have got 4. 6.835 will be exactly midway between 6.83 and 6.84. 6.834 will be closer to 6.83. Hence, on rounding off, we will say that the number we get is 6.83. Next example. Let's say you have got 7.0202 and you wish to round it off to two places after the decimal. So you wish to drop this part. Now, 7.0202 will lie between 7.02 and 7.03. It is closer to which one? So 7.0202 is closer to 7.02. Hence, when we round off 7.0202 to two places after the decimal, we will see it is closer to 7.02 or 7.03 because it lies between them. And as 7.0202 lies closer to 7.02, we will say that on rounding off to two places after the decimal, it will become 7.02. Let's see the next example. If you have got 4.6568 and again you wish to round it off to two places after the decimal, so think of the numbers which are up to two decimal places and between which 4.6568 lies. So the two numbers are 4.65 and 4.66. As 4.6568 is more than 4.655, which will be exactly midway between these two. As this is more than 4.655, this is closer to 4.66. As it is closer to 4.66, it will be rounded off to 4.66. Let's see the next example. If you have got 6.8432, so the two closest number up to two places after the decimal from 6.8432 are 6.84 and 6.85. 6.8432 is closer to 6.84. Hence, after rounding off, we will say that it is 6.84. Moving on to the case of tiebreaker. In the case of complete tie, what is the meaning of complete tie? I will explain. Listen. In the case of complete tie, if the number is exactly midway, for example, if I give you 6.725 and ask you round it off to the nearest number up to two places after the decimal. So you will say, sir, 6.725, it is exactly midway between 6.72 and 6.73. As 6.725 is exactly midway between 6.72 and 6.73, it's a tie. Now I don't know which side this number should go. So we have made a rule, and the rule says this. If you have got, let's say, a number like 6.8750, which is exactly midway between 6.87 and 6.88, then we have a tiebreaker rule. And what does the rule say? If the number preceding 5 is even, we leave it as it is. And if it is odd, we increase it by 1. If the number preceding 5 is even, here it is odd, I know it's 7, is even, we leave it as it is. And if the number preceding 5 is odd, then we add 1 to it. So we will say that when we round off 6.8750, what we get is 6.88. Okay, because this odd number increases by 1. Let's take some example. First example, round off 7.4650 up to 2 places after the decimal. So you will say 7.4650 can be rounded off to 7.46 or 7.47 as both are equally away from 7.4650. So we have a tie. Now the tiebreaker rule says that if the number is exactly midway up to where you have to round off, use this rule. If the number preceding 5 is even, leave it as it is. And if it is odd, add 1 to it. Since 6 is even, we will leave it as it is and the answer will be 7.46. Let's see another example. If you have got 6.1850, 6.1850 is exactly midway between 6.18 and 6.19. So where to round off? Use the tiebreaker rule. The number before 5 is 8, which is even. If the number is even, leave it as it is. So what you get is 6.18. Next, if you have got 6.4750. Now 6.4750 lies exactly midway between 6.47 and 6.48. Think of the number line. But since the number before 5 is odd, you will add 1 to it. So what you will get is 6.48. The last example, 6.8456. 6.8456 is between 6.84 and 6.85. Now tell me, what is the answer? You might be tempted to use the tiebreaker rule, but you shouldn't use it here. Why? Because there is no tie. This 0.8456, this part 56 is closer to 6.85 compared to 6.84. It is more than 0.0050. It is 0.0056. So it is closer to 6.85. As it is closer to 6.85, the answer will be 6.85. Notice everywhere else it was 505050 and here it is 56. So this is not at all the case of tiebreaker. So let's move on to significant figures. Let's say you have this number. So what is this number? This number came from some type of measurement. Somebody measured a length and got it to be 904,032.061. Okay. Now out of all these digits, which digit can have most amount of error? Which digit can you think can be wrong due to measurement? You'll say, sir, the last digit has the highest chance of being erroneous, and this first digit has the least chance of being erroneous, right? So this first digit is called most significant digit and the last digit is called least significant digit. Now we will learn the rules of finding the number of significant figures. So let's start. Rules for finding number of significant figures. The first rule, all non-zero numbers are significant. All the non-zero numbers are significant. So 1, 2, 3, you have got any digit written apart from 0, those are significant. Second, zeros between two non-zero numbers are significant. So if you have got number like 102, 1033, 068. Here the zeros are trapped between two digits, they are significant. Or if you have got 100.608, these zeros are trapped between digit, this zero is trapped between digit, so they are significant. So the second rule says zero between two non-zero numbers are significant. The third rule, leading zeros are insignificant. Leading zeros are insignificant. If I have got 00683 number, then these leading zeros do not make any sense. Leading zeros are insignificant. If you have this number 0.0083, then also the leading zeros are insignificant. Next, in a number with decimal, the trailing zeros are significant. In a number with decimal, the trailing zeros are significant. And let's understand why. Let's say somebody measured a length and reported the length to be 201.65300 meter. Now you will say, what type of an idiot this person is? He should have just said 201.653 meter. What is the sense of writing 00 here? There is a sense. The sense is when a physicist, a scientist write 201.65300 meter, what they mean is that I have used a device so awesome that it can measure up to 5 places after decimal. I have used a device so awesome that it can measure up to 5 places after the decimal. And I got the reading as 00. So I wrote 00. When a scientist write this 201.653 meter, it means that the device used by this scientist is the one which can measure only up to 3 places after the decimal, and this device can measure up to 5 places after the decimal. So it shows that this reading has been made from a better instrument. So remember that in a number with decimal, trailing zeros are significant. In a number with decimal, trailing zeros are significant. The next rule. In a number without decimal, trailing zeros are significant or insignificant depending on the actual way of finding the data. Now, why sometimes we treat the trailing zeros as significant and sometimes as insignificant? This comes from the habits of human being. If I ask any kid how many students are there in your class, they will say 60, 70. They love to round it off. They do not tell the exact number because they do not know. So they just take an estimate and give the answer. Or if I ask them how many students are there in your school, so you will say that the number of students in my school are, let's say, 3,500. You rounded it off. Did you count it? Do you know that it's exactly 3,500? It's not 3,499? No. You just made an estimate. If I ask you how many aspirants write NEET every year, so you'll say, sir, 15 lakh. Was the number exactly 15 lakh? Not a single person more? Not a single person less? So what I'm trying to say here is that human beings have the habit to round off things. That's why we say if you get a reading without actual measurement, then the trailing zeros are insignificant. But let's say NTA is watching everyone registering for NEET and they're looking at registration one by one, and exactly, let's say exactly, luck by chance, exactly 15 lakh people enrolled in the examination. Now, if exactly 15 lakh people enrolled in the examination, how do you know? Sir, we counted. If you have counted and then you are reporting 15 lakh, then beta, the trailing zeros are significant. So the trailing zeros in a number without decimal should be treated as significant or insignificant depends upon they have been measured or not. If the trailing zeros come from an actual measurement, then they are treated as significant numbers. Let's move on. All fixed numbers have infinite number of significant figures. So what do you mean by all fixed number? Let's see with some example. But first of all, let's practice this. How many significant figures are there in 6, 4, 3, 2, 1? So you will say, sir, all the 5, 1, 2, 3, 4, 5 are significant. Hence the number of significant figures are 5. Next example. 9, 4, 3, 3, 2, 6. Sir, all the non-zero digits are significant. And here you have got 1, 2, 3, 4, 5, 6. 6 non-zero digit. So the number of significant figures will be 6. Next example. 106, 106. How many significant figures are there? You will say, sir, the zero trap between two digits is significant. So here all the 6 are significant. Hence the number of significant figures will be 6. Next example. If you have got 101, sir, all the digits are significant apart from 0. And the zero trapped between two non-zero digit is also significant. So all these three 1, 0, 1 are significant. Hence the number of significant figures will be 3. Next, if you have got 10043, how many number of significant figures are there? So you will say, sir, again, digits are significant. The zeros trapped between two digits are also significant. So what I get here is all 5 are significant. Hence the number of significant figures have to be 5. Next, 0067. Sir, leading zeros are insignificant. So here the number of significant figures will be only 2. Next example. If you have got 0.0023, Sir, the leading zeros are insignificant. So the number of significant figures here, these three are not at all significant. So the number of significant figures are only 2. Next question. If you have got 6.400 in a number with decimal, the trailing zeros are significant. Why? Because those trailing zeros are placed there to represent the sensitivity of the device used to make the measurement. So here, when you write 6.400, the trailing zeros are significant. So the number of significant figures here is 4. Next, if you have got 6.20, sir, again, this is a number with a decimal and it has got trailing 0. So all the three are significant. Next example, if you have got 4.630, how many number of significant figures are there, sir? It's a number with decimal, it has got trailing 0. The trailing 0 will be treated as significant. So it has got 4 significant figures. Okay, let's practice a little bit more. Let's say you see somewhere written 6400. How many significant figures are there? It depends upon how the measurement is made. If somebody just gave you a random number 6400 without doing any measurement, then you will say it has got 2 significant figures, because human beings have the habit to round off. But if this 6400 comes from any actual measurement, then we say that all the 4 digits are significant and the number of significant figures will be 4. So 2 or 4 depends upon the source of reading. Personally, if the question comes in NEET, how many significant figures are there in 6400, beta, mark out 2. Have faith, mark out 2. But if they say that some calculation was made and then you got 6400, then the answer has to be 4. Moving on. If they give you 300, the same thing. Answer is 1 or 3 depending upon where this 300 came from. If it came from some approximation, then we will say 1. If it came from some measurement, then we will say 3. So 1 or 3 depending upon the source of reading. Next, the number of eye a healthy human being have is 2. Question is, how many significant figures are there in this 2? For any fixed number, the number of significant figures are infinite. If I ask you, can any healthy human being have 1.99 eyes, or 1.98 eyes, or 1.962 eyes? No, there is no chance of error here. They have to have 2 eyes. How sure are you? I am infinitely sure. Since this number can't be wrong, you are 100% sure, you can take the guarantee and write it as 2.00000000000000000000000 up to infinity. So how many significant figures an exact number have? Infinite. The number of significant figures in an exact number is infinite. Okay, so here you will say in this 2 the number of significant figures are infinite. Let's take one more example. A dozen means 12. If I say I bought, or sorry, I will give you 1 dozen apple. So how many apples do you expect from me? 12, 11.7, or 12.32? How many? You will say, no sir, a dozen means 12. A dozen means exactly 12. That's how it is defined. So when I say I will give you dozen apple, it means exactly 12 apple. Not little bit more, not little bit less. It has to be exactly 12 apple. So a dozen, when we say 12, this 12 has got infinite number of significant figures. Let's move on. How do you add or subtract quantities keeping significant figures in mind? So arithmetic, keeping significant figures in mind. First, do the normal addition subtraction. Whenever you have to add or subtract numbers keeping significant figures in mind, first do your normal addition or subtraction. Then, using rounding off, maintain the same number of significant figures after the decimal. Then, using rounding off, maintain the same number of significant figure after the decimal as there are in the number with least number of significant figures after the decimal. Sir, I haven't understood. We will read it once more and then we will practice the example. So when you are doing addition or subtraction keeping significant figures in mind, step 1, first do your normal addition or subtraction. Then using rounding off, maintain the same number of significant figure in the answer after the decimal as there are in the number with the least number of significant figures after the decimal. Haven't understood, sir? See the example. If I ask you of the number 1.462, how many significant figures this number have after the decimal? We will say, sir, after the decimal 462, okay, 3. It has got 3 significant figure after the decimal. If you add 2.46 to 1.462, how many significant figure after the decimal are present in 2.46? So you will say, sir, there is a 4, there is a 6, so there are 2 significant figures after the decimal. When you add this up, what you get is, do the simple maths. 2, 0, 2, 6, 6, 12, 1 carry over, 4, 5, 4, 9, and 1 plus 2, 3. So you get 3.922. So what you get is 3.922. Now here, the rule says, then using the rounding off, maintain the same number of significant figure in the answer as there are in the number with least number of significant figure after the decimal. So the first number has 3 significant figures after the decimal. The second number has 2 significant figures after the decimal. So the answer should also have 2 significant figures after the decimal. If you want 2 significant figures after the decimal, you will have to drop this third one. To drop it, you have to round off. So round off 3.922 to 2 places after the decimal. What you get is 3.92. Sir, haven't understood. Let's practice more. Let's say I give you 6.383 plus 0.11. So you will say, sir, if you give us 6.383 plus 0.11, the first number has 3 places after the decimal, 3 significant figures after the decimal. The second one has 2 significant figure after the decimal. So the answer should have how many significant figures after the decimal? So the first one has 3, second one has 2. So the answer should have least number, that is 2. So first do your basic maths. Simply add them up. When you add them up, you get 3, 8 plus 1, 9, 3 plus 1, 4. So 6.493. So add them up, 6.493. As the first digit has 3 significant figures after the decimal, second one has 2 significant figures after the decimal, the answer should also have 2 significant figures after the decimal. So as to have 2 significant figure after the decimal, you need to drop this 3. To drop this 3, you will have to round off. You have to round off 6.493 to 2 places after the decimal. It's easy round off. So you will say after rounding off, we will get from 6.493, 6.49. Let's practice one more example. Let's say this time we have got 3 numbers to add. You can see in the first number we have got 2 significant figures after the decimal. In the second one we have got 3 significant figures after the decimal. And in the third one we have got 4 significant figures after the decimal. So simply add them up using your basic maths. When you add them, you get 7.9560. How many significant figures after the decimal the final answer should have? So sir, first one has 2, second one has 3, third one has 4. The least number out of 2, 3, 4 is 2. So the answer should have 2 significant figures after the decimal. But the answer, sir, we got is 7.9560. So you have to round this off to 2 places after the decimal. When you round off 7.9560 to 2 places after the decimal, you will say that 7.9560 can be approximated to 7.95 or 7.96. As it is closer to 7.96, the answer will be reported as 7.96. So we have talked how to add or subtract keeping significant figures in mind. Now we will talk how to multiply and divide. Multiplication and division keeping significant figures in mind. In case of multiplication or division, the answer should have the same number of significant figures. The answer should have the same number of significant figures as the number with the least number of significant figures involved in the calculation. Let's see. First example, Let's say you have got 4.64 into 0.2. First of all, do your basic maths. Take out the calculator, do 4.64 into 0.2, or have faith on me. 4.64 into 0.2 gives you 0.928. The answer should have as many number of significant figures as the number with the least number of significant figures involved in the calculation. So here you will say 4.64 has 3 significant figures, while 0.2, as the leading zeros are insignificant, has only one significant figure. So the answer should have how many significant figures? So the first number has 3, second number has 1. The answer should have as many number of significant figures as the least of the number of significant figures involved in the calculation. So first one has 3, second one has 1. Answer should have 1. So there should be only one significant figure in the answer. But sir, we have got 0.928. This has got 3 significant figures. So we need to drop this to 8 so that the answer has only one significant figure. So we will do rounding off. When we do rounding off, we will report the answer as 0.9. Let's see another example. If they give you 5.6 into 4.92 upon 1.638. How to report the answer keeping the significant figures in mind? So first, do your basic maths and have faith. I have checked it with a calculator. Let's say on calculating, we get this big number. Now, the first number involved in calculation has got 2 significant figures. The second number involved has got 3 significant figures. The third number involved has got 4 significant figures. Question is, how many significant figures should be present in the answer? So sir, first one has 2, second one has 3, third one has 4. So answer should have the least number of significant figures as in any one of the reading involved in the calculation. So answer should have 2 significant figures. So what to do to get 2 significant figures? So round it off. You have to keep the first 2, the most significant part. So you will have to round off this part. When you round this off, you will round this off to 16 or 17. You will say, sir, as 16.82 is closer to 17 compared to 16, we will report the final answer as 17. So next example. If you have got 6.21 into 4.832, what will you finally get? So you will say, sir, first let's do the basic maths. Let's say we calculated 30.00672. Okay, this is what we get. The first one here has got 3 significant figures. The second number here has got 4 significant figures. How many significant figures should be present in the answer? So the least of them, that is 3. So how to round off this number so that the final answer has got 3 significant figures? So sir, keep 3, you have to keep 0 and this 0 and drop out this part. So by rounding off, drop out the remaining part so that you have got 3 number of significant figures after rounding off. So what we get is 30.0. The next one, if you have got 4 into 6.8, this is a tough one, 4 into 6.10. What do you get on multiplying? Sir, we get 27.2. The first one has 1 significant figure. The second one has 2 significant figures. So the answer should have only 1 significant figure. How should I write 27.2 so that the answer contains only 1 significant figure? So think of the number closest to 27.2 which can have 1 significant figure. It can either be 20 or 30. The numbers closest to 27.2 which have only 1 significant figure are 20 and 30. So round off 27.2 such that the answer contains only 1 significant figure, and that answer will be 30, because here the trailing 0 won't be considered. The trailing 0 won't be considered as significant. So let's move on. If the side length of a square is 1.2 meter, what is its perimeter? If the side length of a square is 1.2 meter, what is its perimeter? Taking care of significant figure. So you might know that if you have a square of side length A, then the perimeter of square is nothing but 4 times A. So here you will say the perimeter will be 4 times 1.2. 4 times 1.2, when you do the basic maths, you get 4.8. The number of significant figure in 4 is 1 and in 1.2 is 2. So the answer should have how many number of significant figure? 1. So what we do here is we round off 4.8 so that we get only one significant figure, and that will be equal to 5. This is the wrong approach to this question. Don't solve this question this way. Why? When I say a square has got 4 sides, can the number of side of square will be 3.99? Can the number of side of square be 4.01 or 4.02? No, sir, it's an exact number. The number of side of a square is 4, exactly 4. So question is, how many number of significant figures this 4 in the formula p equals to 4a have? So this 4 has got infinite number of significant figures. So here 4 is a fixed number. So the number of significant figures in it are infinite. So we say 4 times of 1.2 is 4.8. The 4 has got infinite number of significant figure. 1.2 has got 2. The answer should have least number of significant figures. So answer should have at least 2 significant figures. And there are already only 2. So should have 2. We will report the answer as 4.8. And this first solution was a wrong solution. Moving on. Now we will talk about errors. Whenever we talk about errors, we divide it into two families. There is something called systematic error and there is something called random error. When I heard the term systematic error for the first time in my life, it sounded like an oxymoron. I was like, systematic error, an error which is systematic. How can error be systematic? For example, let's say you are measuring the length of a table. But the scale you are using, which is meant to be 15 centimeter long, is actually 14 centimeter long. So there are calibration issues with this scale. So it is meant to be 15 centimeter long, but actually the manufacturer made it wrong and now it is actually 14 centimeter long. And if you are measuring the length of this table using this scale, no matter how many times you take the reading, you take it once, you take it twice, you take it twice, you keep on measuring 1,000 times. As your instrument is wrong, every single time you will get an error. Moreover, since there is a particular amount of deficit which will be created in each reading, the reading will be every time smaller. Okay, so this will measure less but report more. This will measure less because the actual length is 14, but you will see markings and you will read 15. So this will measure less and report more every time. So all the errors produced by such a scale are systematic. No matter how many times you take the reading, the same error keeps on creeping in every reading. So systematic errors are the one which systematically creeps in every reading. I have told you already how can you get systematic error. You can get systematic error if your instrument is not properly calibrated. Now listen to the next thing which I am going to say. All of us know that kinetic energy is equals to half mv square. But let's say a student of class 11th is doing some experiment. He bought a cheap book, and in that cheap book the formula of kinetic energy is given as half vm square. Maybe while typing, somebody typed it wrong. Now this student who bought this book, who learned the formula from this book which is wrong, finds the mass of the ball, finds the speed of the ball, applies the formula, calculates the kinetic energy. Is the formula being applied by a student right? No, it's wrong. So will the reading produced by him will have errors? Obviously. But no matter how many times he measures the mass, no matter how many times he measures the speed, till the time he or she is using the wrong formula, they will keep on getting the wrong answer again and again and again. When you keep on getting the same wrong answer every time, it is called systematic error, because your error is very systematic. So, can instruments produce systematic error? Yes. Instruments can produce systematic error if they are not properly calibrated. Can human beings do systematic error? Yes. When they do not know the proper procedure to do the experiment. The next type of errors we will talk about is random error. Random error are just random. They happen sometime. I did a big calculation, did it properly, I got the answer as 1.57, but while bubbling, I bubbled 1.75. This has happened with you, right? So these type of errors are random. Will the same error happen again? No. Maybe means they are random. They can happen, they can't happen. If let's say you are doing an experiment in lab and there is galvanometer, resistor and everything. Suddenly there is a voltage fluctuation in the supply line. So your reading might get fluctuated. This is also random error. This won't happen every time. It happened once. It won't happen in every reading and you can't predict in which reading it will happen. So they are random errors. Humans can do both systematic error as well as random error. To err is human. Human beings have got capability to do both random error as well as systematic errors. We can minimize random error by taking more number of readings. You can't minimize systematic error by taking more number of readings because systematic error creeps into every reading in the same direction by the same magnitude, while random errors can be minimized by taking more number of readings. Also, the random error in a reading is inversely proportional to number of observation. So if you double your number of observation, the random error becomes half. If you triple the number of observation, the random error becomes 1/3. So random error that you will get in a reading is inversely proportional to the number of observations. I asked this question to all students. Can you buy me 1 kg of sugar? Can you please buy me 1 kg of sugar? Please. Answer is no. No one can buy exactly 1 kg of sugar. Sir, I have bought it many times. No. If you are saying that I have exactly bought 1 kg of sugar, it means that you have exactly 1.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000There has to be minutest of error. Even if you used a weighing scale which can measure up to 10 places after the decimal, very nice scale, then you don't know what are the digits after that. No one can buy exactly 1 kg of sugar. It has to be slightly more than 1 kg or slightly less than 1 kg. You can't buy exactly 1 kg of sugar. So every reading that we take has some error in it. A famous statement by Sir Walter Lewin: the knowledge of a measurement of quantity without the knowledge of error in the measurement is meaningless. The knowledge of the measurement of a quantity without the knowledge of error in measurement is meaningless. So you have measured something, but you don't know what can be the scope of error in this measurement, then your measurement is of no use. Now, when you buy something, on that packet, it's written 2 kg. And somewhere down in the packet, it's written plus minus 5% error. Why? Because when you buy a product, the seller knows they are incapable of exactly measuring 2 kg and supplying it to you. So there are always some scope of error. So they write underneath the packet plus minus 5% error. It means that within this packet, you can have up to 5% more than 2 kg or up to 5% less than 2 kg. It won't happen that you bought this packet and this packet has got only 0.75 kg of content. The range of error in what they have mentioned will be at most plus minus 5%. So if I tell you I have bought sugar and I have bought 2 kg plus minus 0.01 kg of sugar. Then when I say I have 2 plus minus 0.01 kg of sugar, it means that the maximum amount of sugar that I might have is 2 plus 0.1, that is 2.01 kg, and the minimum amount of sugar that I might have is 2 minus 0.01, that is 1.99 kg. If I say that I have bought 2 kg plus minus 0.01 kg of sugar, I can have any amount of sugar between 1.99 kg and 2.01 kg. Similarly, if I say I have measured this length and found it to be 5 plus minus 0.2 meter, this means that the length can be maximum equal to 5 plus 0.2, that is 5.2 meter, and minimum equal to 5 minus 0.2, that is 4.8 meter. So the length can be anywhere between 5.2 meter and 4.8 meter. Now let's learn about relative error. So if you have a quantity which is measured and you find that the quantity is written as A plus minus delta A, then the first quantity A is called the absolute value and the part delta A is called absolute error. So A is absolute value and delta A is absolute error. Now we need to define a term called relative error in the calculation. The relative error in a calculation is nothing but absolute error by absolute value. So that is delta A by A. Error doesn't matter. The relative error in the calculation matter. If let's say I am measuring the height of Mount Everest and I did an error in the calculation of the height of Mount Everest by 10 meter, I won't be put into jail for this. But if I am making a building and I reduce the overall height of building by 10 meter, that's a big error. So an error in measurement of 10 meter doesn't make the amount of error same. It also depends upon what you are measuring. If you are measuring the height of Mount Everest, then an error of 10 meter is a small error. When you are measuring the height of one building, then the error of 10 meter is a big error. So error doesn't matter, relative error matters. Next, we have got another term called percentage error. Percentage error is nothing but relative error into 100. So percentage error is nothing but relative error into 100. So let's talk about a term that will be used very widely later, that's called least count. Least count. The minimum that the device can measure is called the least count of the device. So just by looking at the measurement taken by a device, we can tell its least count. Seriously, sir? Yes. Let's see an example. If the petrol pump meter reads 10.75 liter, what is the least count of this particular meter placed inside the device? So you'll say, what is the least count of this meter? The minimum reading you can get is 0.01 liter. Sir, how do you know? See, the reading of meter is 10.75 liter. Yes. So this meter can measure up to 2 places after the decimal. If this can measure up to 2 places after the decimal, the minimum you can measure is 0.01 liter. Right? Let's see more example so that you will get confident. Determine the least count of following reading. If let's say you find reading of 6.83 meter. If somewhere you have a reading of 6.83 meter, what is the least count of the device used to make this reading? So you will say this device can measure up to 2 places after the decimal. So the minimum reading it can measure is 0.01 meter. Let's see next example. If you measured the mass of something and found it to be 4.854 kg. What is the least count of the device used to make this measurement? So you will say this device can measure up to 3 places after the decimal. So the minimum amount it can measure is 0.001 kg. If you get reading of 6.942 gram, what is the least count of the device? The least count of device will be 0.001 gram, as it can measure up to 3 places after the decimal. When the error in a reading is unknown, listen to this carefully. When the error in a reading is unknown, we take the least count of the device as the absolute error. When the error in a reading is unknown, we take the least count of the device as the absolute error. For example, it means a measurement of 1.53 meter should be reported as 1.53 plus minus 0.01 meter. If you get a reading of 1.53 meter, it means that the device you have used can measure up to 2 places after the decimal. So the minimum you can measure using this device is 0.01 meter. When the error in a reading is not known and you have got only single reading, then the least count of the device used to make the measurement is taken as the absolute error and you report the answer as 1.53 plus minus 0.01 meter. Let's continue. So, if you get reading as 6.32 kg, it should be reported in the proper error limit as 6.32 plus minus 0.01 kg. If you measure time to be 946.56 second, it should be reported as 946.56 plus minus 0.01 second. Now, how to do arithmetic taking care of errors? Let's say we have a rod of length 5.3 plus minus 0.1 meter. When I say that this rod has got length of 5.3 plus minus 0.1 meter, its length can be anywhere between 5.4 and 5.2. 5.3 plus 0.1 is 5.4. 5.3 minus 0.1 is 5.2. Let's say we have got another rod of length 2.8 plus minus 0.2 meter. So the length of the second rod can be anywhere between 3 meter, 2.8 plus 0.2, and 2.6 meter, that is 2.8 minus 0.2. Now let's say we place both the rod end to end. If we place both the rod end to end, the total length will be L1 plus L2. What can be the range of value of L1 plus L2? So you will say, you will get the maximum possible sum of length if the length of first one is maximum and the length of second one is maximum. So the maximum possible length you will get on placing these two rods will be 5.4 plus 3, that will be 8.4. And the minimum possible length of this combination of two rods will be the minimum possible length of first rod plus the minimum possible length of second rod. The minimum possible length of first rod is 5.2, second rod is 2.6. So the minimum possible length of combination is 5.2 plus 2.6, that is 7.8. As the length finally is found to be somewhere between 7.8 and 8.4. 7.8 and 8.4 has a gap of 0.6. So you can find their average and you can say, I can report these two lengths as 8.1 plus minus 0.3. 8.1 plus minus 0.3. So when you do 8.1 plus 0.3, you get 8.4. When you do 8.1 minus 0.3, you get 7.8. So if you need to add up two lengths, just add up their absolute part. So 5.3 plus 2.8 gives you 1 here, 1 goes carry over, 5, 6, 7, 8, 8.1. And add up their error part. 0.1 plus 0.2 gives you 0.3. Simple. So if you need to add up two quantities having certain error, simply add up the absolute part and add up the error part. So easy. Now let's say we need to find L1 minus L2. When you will find the maximum possible value of L1 minus L2? From the first length, we are subtracting the second length. If you want the difference in the length to be maximum, take the maximum possible first length and the minimum possible second length. When you take the maximum possible first length and minimum possible second length, the difference is maximum. 14 minus 6 gives you 8. Here you have got now 4. 4 minus 2 gives you 2. So the maximum possible difference in length is 2.8. How to find the minimum possible difference in length? L1 minus L2 will be minimum when you take the minimum value of L1 and maximum possible value of L2. L1 minus L2, the gap in the two lengths, will be minimum when you do 5.2 minus 3, and 5.2 minus 3 is 2.2. Hence, the maximum possible difference is 2.8 and the minimum possible difference is 2.2. How can you report it as a single answer? You will say, if I think of 2.5 plus minus 0.3, 2.5 plus 0.3 gives you 2.8, 2.5 minus 0.3 gives you 2.2. So the length range of 2.2 to 2.8 can be reported as anything 2.5 plus minus 0.3. Now I want to emphasize here, when you add up L1 and L2, you add up the absolute part, you get 8.1. You add up the error part, you get 0.3. But when you are finding their difference, you subtract the absolute part, 5.3 minus 2.8, here you get a 5, 4 minus 2, you get a 2.5. So the absolute part gets subtracted, but the error part is not subtracted, it is added. You again get 0.3. So remember the world famous statement, errors always add up. When you add up multiple numbers having some error in their calculation, the absolute part add, the error part add. But when you are subtracting them, in the absolute part you subtract, but in the error part you again add. That's why we got here 0.3. So if we have two numbers A written as A plus minus delta A and another measurement B which is reported as B plus minus delta B, then when you do A plus B, you add up the absolute part A plus B and you add up the error part delta A plus delta B. But when you are finding the difference, when you are finding A minus B, you subtract the absolute part A minus B, but the error again adds up delta A plus delta B. So remember the statement, errors always adds up. Okay, let's do an example to understand this further. A shopkeeper gives you 478 gram of sugar and you return 253 gram. Determine the sugar with you with proper error limits. Sir, you haven't given me error part. You have just said that shopkeeper gives you 748 gram of sugar and you return 253 gram of sugar. How will I know what is the error part? If in a particular measurement the error is not given, then you take the least count of the device used to take the reading as the error. So here the least count of the device is 1 gram. The minimum you can measure using this device is 1 gram. So the mass given to you should be taken as 748 plus minus 1 gram. And the mass returned by you should be taken as 253 plus minus 1 gram. So shopkeeper gave you 748 plus minus 1 gram. You returned 253 plus minus 1 gram. So how much you have left with you? So you will simply subtract. Hence the mass that is still with you is 748 plus minus 1 minus 253 plus minus 1. Here we are subtracting. So the absolute part you will subtract, but the error part will get added. So what you will be left with is 748 minus 253 plus minus 1 plus 1. So you get 495 plus minus 2 gram. Okay. So we have seen error in addition and subtraction. Now we will talk about errors in multiplication and division. So let's say we have a quantity z such that z equals to k a raised to the power of alpha b raised to the power of beta upon c raised to the power of gamma. For small errors, we can say that delta z by z equals to alpha delta a by a plus beta delta b by b plus gamma delta c by c. Now you will say, sir, few days back you taught us about change. There you placed here a minus sign. Now today you are placing here a plus sign. Errors always add up. That's why I'm placing here a plus sign. Keep this in mind. So this quantity delta z by z represents what? It represents relative error in calculation of z. Similarly, what is delta a by a? Relative error in calculation of a, delta b by b, relative error in calculation of b, and so on. So if we know the relative error in mass and speed, we can find the relative error in the kinetic energy and momentum, because we can write kinetic energy equals to half mv square. So delta ke by ke equals to delta m by m plus 2 delta v by v, right? Also, if we multiply each term with 100, so this first term becomes percentage error in measurement of z. This delta a by a into 100 becomes percentage error in measurement of a, and so on. Okay. So let's look at its usage. So let's see a problem. These are simple things. If the percentage error in calculation of mass and speed is 1% and 2%, find the percentage error in calculation of kinetic energy. So you can say, sir, we know that kinetic energy is half mv square. We can say, using the formula, if z equals to k a raised to power of alpha b raised to power of beta upon c raised to power of gamma, then delta z by z equals to alpha delta a by a plus beta delta b by b plus gamma delta c by c. I can say that the relative error in measurement of kinetic energy equals to relative error in measurement of mass plus 2 times the relative error in measurement of speed. Multiply each term with 100. What we get is the percentage error in measurement of kinetic energy equals to percentage error in measurement of mass plus 2 times the percentage error in measurement of speed. The percentage error in measurement of mass is given as 1. The percentage error in measurement of speed is given as 2. So we will say the percentage error in measurement of kinetic energy equals to percentage error in measurement of mass, which is 1%, plus 2 times the percentage error in measurement of speed, that is 2%. So 1 plus 2 times of 2, that gives you 5% error. Simple. Let's practice more. If the percentage error in calculation of mass and side length of a cube is 1% and 0.5%, find the percentage error in the calculation of density. We did the same type of question for small percentage changes. Here we are not talking about small percentage changes. Here we are talking about error. So we know that for a cube, the density of cube equals to mass by side length whole cube, mass by volume, and the volume of cube is side length whole cube. So we can say density of a cube equals to mass upon a cube. Using the same formula, we will say delta rho by rho into 100 equals to delta m by m into 100 plus because errors always add up, plus 3 times delta a by a into 100. Delta rho by rho into 100 represents percentage error in calculation of density equals to percentage error in calculation of mass plus 3 times the percentage error in calculation of side length. Percentage error in calculation of mass is 1% and percentage error in calculation of side length is 0.5%. So you get percentage error in measurement of density equals to percentage error in calculation of mass, which is 1%, plus 3 times the percentage error in calculation of side length, which is 0.5. So you get 1 plus 3 times of 0.5. So 1 plus 1.5, that becomes 2.5 percentage error. Let's practice next example. If the percentage error in calculation of time period and length of the simple pendulum is 2% and 1%, if the percentage error in calculation of time period and length of simple pendulum is 2% and 1%, find the percentage error in calculation of G. So we know that time period equals to 2 pi under root L by G. Square both the side, you get T square equals to 4 pi square L by G. From here you can rearrange and write G, bring the G up here, equals to 4 pi square L upon T square. Now use the formula. You will say delta G by G equals to delta L by L plus 2 delta T by T. Sir, why the plus sign? Because errors always add up. So relative error in measurement of G equals to relative error in measurement of length plus 2 times the relative error in measurement of time period. If I multiply each term with 100, I get percentage error in calculation of G equals to percentage error in measurement of length plus 2 times the percentage error in measurement of time period. Percentage error in measurement of length is given to us as 1%. And percentage error in measurement of time period is given to us as 2%. So we will say percentage error in measurement of G equals to 1 plus 2 times of 2, that becomes 5% error in the measurement of G. Let's move on. So now, the next example, if the length and width of a rectangular field is 20 plus minus 0.1 meter and 10 plus minus 0.1 meter, determine the area of the field with proper error limit. So, length of field is given as L plus minus delta. Width of field is given as B plus minus delta V. Here the length is given as 20 plus minus 0.1 meter, while the width is given as 10 plus minus 0.1 meter. If you need to find the area, you simply find out length into width. So So you say that area which will be coming out as a plus minus delta a when we find with the proper error limit, we can say that area equals to length into width. The length is 20, the width is 10. So the absolute part of area will be nothing but the absolute length into absolute width. So the absolute part of area will be simply 20 into 10, that will be 200 meters square. Now how to find the error part? Look here, you know that area equals to length into width. So you can say that delta A by A equals to delta L by L plus delta B by B. Delta A by A represents the relative error in the measurement of A. We already know that A will be 200. We need to find delta A. We already know that delta L is 0.1 and L is 20. Delta B is 0.1 while B is 10. So substituting the data, we can say delta A by 200 equals to 0.1 by 20 plus 0.1 by 10. So multiply 200 to each term. When you multiply 200 to each term, you get delta A equals to 1 plus 2, which is nothing but 3. So you will report the final answer as, so the area should be reported as absolute part 200 plus minus the absolute error part 3. So the area should be reported as 200 plus minus 3 meters square. Now let's see the next example. If the mass and speed of a ball is 5 plus minus 0.1 kg and 100 plus minus 1 meter per second, find its kinetic energy with proper error limit. So first of all, find out what will be the absolute value of kinetic energy using the formula kinetic energy is half mv square. So we know that kinetic energy equals to half mv square. To find the absolute value of kinetic energy, substitute the mass as 5 and speed as 100. So when you substitute this, you get half into 5 into 100 square. Half into 5 into 100 square becomes 25,000 joule. This is the absolute value of kinetic energy. But we need to report here kinetic energy with proper error limit. So we will say delta Ke by Ke equals to delta M by M plus 2 delta V by V. We already know what is Ke, 25,000. They have given me delta M as 0.1 and mass as 5. Delta V as 1 and V as 100. So substituting the data, we get delta Ke by 25,000 equals to 0.1 by 5 plus 2 into 1 by 100. So as to find delta Ke, multiply 25,000 on the right hand side. So what you get is 500 plus 500. Do the calculation, it's right. So you get the error in the measurement of kinetic energy is nothing but 1000. So we can report the kinetic energy with proper error limit as 25,000 plus minus 1000 joule. So 25,000 joule can be thought of as 25 kilojoule. 1000 joule can be thought of as 1 kilojoule. So you can report the answer as 25 plus minus 1 kilojoule. Simple. Now let's see a very important case because it is mentioned in NCERT. How to find the equivalent resistance with proper error limit when the resistances are connected in parallel. Let's say we have got two resistances in parallel and their resistances are given as R1 plus minus delta R1 and R2 plus minus delta R2. And we need to find their equivalent resistance with proper error limit. We know that for resistances in parallel, 1 by R equivalent equals to 1 by R1 plus 1 by R2. Now we have learned that we can write 1 by X as X raised to the power of minus 1. So I can say that R equivalent raised to the power of minus 1 equals to R1 raised to the power of minus 1 plus R2 raised to the power of minus 1. Differentiating out each term, I will say dr equivalent raised to the power of minus 1 equals to dr1 raised to the power of minus 1 plus dr2 raised to the power of minus 1. What is the differentiation of x raised to the power of n? The differentiation of x raised to the power of n is n x raised to the power of n minus 1 dx. So the differentiation of r equivalent raised to the power of minus 1 will be minus 1 r equivalent raised to the power of minus 1 that is minus 2 dr equivalent. Similarly, the differentiation of r1 raised to the power of minus 1 will be minus 1 r1 raised to the power of minus 2 dr1. and the differentiation of r2 raised to the power of minus 1 will be minus 1 r2 raised to the power of minus 2 dr2. Now I can write this r equivalent raised to the power of minus 2, r equivalent raised to the power of minus 2 as 1 upon r equivalent whole square, and we can cancel out this minus 1 minus 1 minus 1 from each term. So what we get is dr equivalent upon r equivalent whole square equals to dr1 by r1 square plus dr2 by r2 square. Here what is dr equivalent? The infinitely small error in measurement of r equivalent. Approximating infinitely small error to small error, we will say delta r equivalent upon r equivalent whole square equals to delta r1 upon r1 square plus delta r2 upon r2 square. So when they give you two resistances in parallel, first find out the R equivalent using this formula. Once you know R equivalent, substituting the value of delta R1, R1, delta R2, R2, you can find delta R equivalent. So let's practice question to understand this better. The question says, we have two resistors, the first one of 6 plus minus 0.09 ohm and second one of 3 plus minus 0.09 ohm. So you have got two resistors. Find the equivalent resistance when they are connected in series and parallel. So what will be the equivalent resistance of these two resistors when they are connected in series and when they are connected in parallel? So series part is easy. So when they are connected in series, R equivalent is simply equal to R1 plus R2. So as R equivalent equals to R1 plus R2, you will simply write it as 6 plus minus 0.09 plus 3 plus minus 0.09. So add up the absolute part and add up the error part. So what we get is 9 plus minus 0.18 ohm. 0.09 plus 0.09 gives you 0.18. Simple. The complicacy, a little bit of it, is in parallel and it is mentioned in NCERT, so you should know. Now let's think of the parallel case. Before you solve further, before you use the formula that delta R equivalent upon R equivalent whole square equals to delta R1 upon R1 square plus delta R2 upon R2 square, I suggest you to first find out the value of R equivalent. To find out the value of R equivalent, use the formula 1 by R equivalent equals to 1 by R1 plus 1 by R2. Substitute R1 as 6 and R2 as 3. So when you substitute them, 1 by R equivalent equals to 1 by 6 plus 1 by 3, you get that R equivalent is 2. Now to find the delta R equivalent part, you will say that delta R equivalent upon R equivalent whole square equals to delta R1 upon R1 square plus delta R2 upon R2 square. You already know that R equivalent is 2. You know that delta R1 is 0.09. R1 is 6. Delta R2 is 0.09. R2 is 3. Substitute the data and find out delta R equivalent. So you will say delta R equivalent upon 2 square equals to 0.09 by 6 square plus 0.09 by 3 square. So multiplying this 2 square on both the sides and solving, you get that delta R equivalent is 0.09 into 4 by 36 plus 0.09 into 4 by 9, which on solving you get 0.01 plus 0.04, which is 0.05. So the final answer should be reported as R equivalent plus minus delta R equivalent. So that will be 2 plus minus 0.05. Easy. That's all in this session. See you guys in the next session. Bye bye. Hope you like this session. Stay tuned to Scomore.